divide and conquer algorithms and recurrence relations. Many recursive algorithms take a problem with a given input and divide it into one or more smaller problems. This reduction is successfully applied until the solution of the smaller problems can be found quickly. For instance, we perform a binary search by reducing the search for an element in a list to the search of this element in a list half as long. We successfully apply this reduction until one element is left. This procedure follows an important algorithmic paradigm known as divide and conquer. Divide and conquer algorithms divide a problem into one or more instances of the same problem of smaller size, and they conquer the problem by using the solution of the smaller problems to find the solution of the original problem, perhaps with some additional work. In this section, we will show how recurrence relations can be used to analyze the computational complexity of divide and conquer algorithms. We will use these recurrence relations to estimate the number of operations used by different divide and conquer algorithms. Divide and conquer recurrence relations. Suppose that a recursive algorithm divides a problem of size n into a subproblems where each subproblem is of size n divided by b. For simplicity, assume that n is a multiple of b. In reality, we will take the floor or the ceiling of n over b. Also, suppose that a total of g of n extra operations are required in the conquer step of the algorithm to combine the solutions of the subproblems into a solution of the original problem. Then, if f of n represents the number of operations required to solve the problem of size n, it follows that f satisfies the recurrence relation f of n equals a times f of n over b plus g of n. This is called a divide and conquer recurrence relation. We will first set up the divide and conquer recurrence relation that can be used to study the complexity of some important algorithms. Then we will show how to use this divide and conquer recurrence relation to estimate the complexity of these algorithms. Example 1, binary search. We covered binary search algorithm in the study guide of test 2. This binary search algorithm reduces search for an element in a search sequence of size n, which is already ordered, to a binary search for this element in a sequence of size n divided by 2 when n is even. Hence, the problem of size n has been reduced to one problem of size n divided by 2. Two comparisons are needed to implement this reduction, one to determine which half of the list to use and the other to determine whether any term in the list remain. Hence, if f of n is the number of comparison required to search for an element in a search sequence of size n, then f of n is equal to f of n divided by 2 plus 2 when n is even. That is, a is equal to 1 and b is equal to 2 and g of n is equal to the constant function 2. Example 2. Finding the maximum and minimum of a sequence. In this example, the sequence is not sorted in the beginning, and we want to find the maximum and the minimum element. Consider the following algorithm for locating the maximum and minimum elements in a sequence A1, A2, and so on an. If n is equal to 1, then A1 is the maximum and also the minimum of the sequence. If n is bigger than 1, split the sequence into two sequences each, either with both have the same number of elements or one of them has one more element than the other. The problem is reduced to finding the maximum and the minimum of each of these two smaller sequences. The solution to the original problem results from the comparison of the separate maximum and minima of the two smaller sequences to obtain the overall maximum and minimum. Let f of n be the total number of comparisons needed to find the maximum and minimum elements of the sequence with n elements. We have shown that a problem of size n can be reduced into two problems of size n divided by 2 when n is even, using two comparisons, one to compare the maximum and one to of the two the maximum of the two sequences, and one to compare the minima of the two sequences. This gives us the recurrence relation f of n equals 2 times f of n divided by 2 plus 2 when n is even. Recurrence relations of the form f of n equals a times f of n divided by b plus g of n arise in many different situations. It is possible to derive estimates of the size of the function that satisfy such a recurrence relation. Theorem 1. Let f be an increasing function that satisfies this recurrence relation. F of n equals a times f of n divided by b plus c when n is divisible by b, where a is at least 1 and b is an integer greater than 1, and c is a positive real number. Then f of n is b co n to the power logarithm to the base b of a if a is bigger than 1, and equal to b co of logarithm of n if a is equal to 1. Furthermore, when n is equal to b to the power k and a is not 1, where k is a positive integer, f of n is equal to c1n to the power logarithm to the base b of a plus c2, where c1 and c2 are given with these formulas. This theorem is proof in the book. We are not considering the proof. We are only required to know how to use the theorem for different recurrence relations. The next example illustrates how theorem 1 is used. In the first example, f of n is 5 times f of n divided by 2 plus 3, and f of 1 is 7. Find f of 2 to the power k, where k is a positive integer. Also, estimate f of n if f is an increasing function. So, we have a equals 5, b equals 2, and c equals 3 in the recurrence relation of the theorem. We see that if n is equal to 2 to the k, then we can apply this result. And in that case, n to the power logarithm to the base b of a is this. Replace n with b to the k. But b to the power logarithm to the base b of a is just a, so this results in a to the k. That is f of n is equal to a to the k, c1 plus c2. And c1 and c2 can be computed easily because f of 1 is given and c and a are given. We obtain this. As a result, f of n is 5 to the k, 31 times 31 fourths minus 3 fourths. If f is an increasing function, then theorem 1 shows that f of n is bcol n to the power logarithm to the base b of a, that is bcol of n to the power logarithm to the base 2 of n. So if the base is missing, it is 2. We can use theorem 1 to estimate the computational complexity of the binary search algorithm and the algorithm given in example 2 for locating the minimum and maximum of a sequence. Give a bcol estimate for the number of comparisons used by a binary search. Assuming that f is an increasing function, we can use this recurrence relation. Where f is the number of comparisons required to perform a binary search on a sequence of size n. Hence, from theorem 1, because a is 1 and b is 2, c is 2, we obtain that f of n is bcol logarithm of n. In the next example, give a bcol estimate for the number of comparisons used to locate the maximum and minimum elements in a sequence using the algorithm from example 2. Solution. We know that f of n is 2 times f of n divided by 2 plus 2 when n is even, where f is the number of comparisons needed by this algorithm for a sequence of size n. Hence, assuming again that f is an increasing function, theorem 1 applies with a equals 2, b equals 2, and c equals 2. So, logarithm to the base b of a is logarithm to the base 2 of 2, which is 1. Therefore, f of n is b of n.